Hello guys, welcome back to my channel. I am Shams Fatima from Sri Venkateshwara College of Engineering, Bangalore. And today we are going to speak about software testing. And the topic inside the software testing is variations on mutation analysis. So there are basically three cases of variation on mutation analysis. The first one is that it kills the mutants based on the output produced by execution of test cases, and hence it's called as strong mutation. Moving ahead to the second case, it can generate a number of mutants quadratic in the size of the program. Each mutant must be compiled and executed with each test case until it is killed. Moving ahead with the third case, the time and the space required for compiling all the mutants and for executing all the test cases for each mutant must be impractical. Now, we are gonna estimate the population sizes. Counting fishes. Let us consider the lake, which is inhabited by two kinds of fishes. The first one is the native trout, and the second one with the species of chub. The Fish and the Wildlife Services wishes to estimate the population to evaluate their efforts to eradicate the chub without harming the population of native trout. Here, basically, the chub can be estimated statistically as follows. Consider 1,000 chubs which are to be netted. Their fins are marked by attaching a tag. Then they are released back into the lake. Over the few next weeks, the fishermen are asked to report the number of tagged and untagged chub which are being caught. If 50 tagged chubs and 300 untagged chubs are caught, we can calculate, and thus there are about 6,000 untagged chubs remaining in the lake. And the formula which is being used is 1,000 divided by untagged chub population is equal to 50 by 300. It is very interesting to know about the calculation to estimate the ratio between the chub and the trout. Let's move ahead to the next estimation population size, that is nothing but counting residual faults. A similar procedure can be used to estimate the number of faults in the program. Here, seed a given number of S of faults in the program. Test the program with some test suits and count the number of revealed faults. Measure the number of seeded faults detected as DS and also the number of natural fault detected as DN. Estimate the total number of faults remaining in the program. Assume the test suit is effective at finding number of faults as it is finding at the seeded faults. So here is the formula, that is S divided by total number of natural faults is equal to ds, that is estimated faults, divided by dn, those are the natural faults. Here we have to estimate the number of faults remaining in the program by determining the portion of the seeded faults. Estimate the trout population by counting the chub. The seeded faults are the chub and the real faults are the trout. Here, we must either have a good reason for believing, make adequate allowance for uncertainty. The difference is that we cannot avoid the problem by repeating the process with the trout. Once the fault has been detected, our knowledge of its presence cannot be erased. We depend, therefore, a very good fault model so that chubs are as representative as possible of trout. Here, the test cases has to be designed and detected for a particular seeded faults. Then statistically, estimation of total population of fishes or errors cannot be justified. Hope you got some information from my video about variation on mutation analysis.